In this video, we're going to talk about the Maxwell speed distribution. The Maxwell speed distribution is the number of particles or percentage of particles in some ideal gas that are moving with a specific speed. So you can imagine that you have some particles in a box, and these particles are all moving around randomly, and each of them has some speed associated with them. They're not all moving at one exact speed. And in fact, we are going to figure out a distribution of what is the most likely speed for a particle in a given gas, depending on the temperature of that gas. So for example, at room temperature, molecules move at a few hundred meters per second on average, which is pretty fast. If you're very, very low temperature, the particles will be moving much slower, and of course if you're at a very, very high temperature, the particles will be moving much faster. So what we're going to do is we are going to start out by talking about a probability, but we need to turn our sum. So normally our probability would be equal to sum of the Boltzmann factor divided by the partition function. Which is what we have here. We have our degeneracy multiplied by our Boltzmann factor, where the energy of the particle, we're assuming there's only kinetic energy, so the energy is a function of velocity, divided by our Boltzmann factor, and we have turned our sum over the velocity into an integral. And we can do that because the velocity is actually a continuous variable. There's not a discrete velocity levels like there are discrete energy levels. The velocity can take on any value that it wants. We are not worried about the direction of the velocity, so we're only dealing with absolute magnitude of the velocity or the speed here. Okay, so what we'd like to be able to figure out is we'd like to be able to write the energy here in our Boltzmann factor in terms of velocity explicitly, which we can do by simply noting that we're only worried about kinetic energy, which means that we have mv squared, 1/2 mv squared. Our energy function is mv squared over 2, so we can simply plug that in. That is our Boltzmann factor. The degeneracy is a little bit more tricky. So the degeneracy of a velocity state, a state with a set velocity, can be thought about in terms of a plot like this. So first, let's think about just 2 dimensions. So if I have a gas in only 2 dimensions, I can have some Vx value and some Vy value. And what I know is that if I write down a vector that has some set velocity, say 20 meters per second, that the length of the velocity vector in this velocity space will be 20 meters per second. And so my question is, how many possible vectors are there that have a speed of 20 meters per second? Well, if I look here, here's one possible vector, but there's another vector that points only in the x direction, right? That has the same speed, 20 meters per second. There's another vector that points only in the y direction, and there's another one that points over here, etc. So what we need to do is we need to add up all of these vectors, and it turns out that the way to do that is simply to take the length of this line, because each of my possible vectors is associated with a specific point on that line. So the length of the line is equal to my degeneracy, the number of possible states there are with a given velocity. Now, we don't want to work in 2 dimensions, we want a 3-dimensional gas. So we have 3 potential components of our vector, right? Vx, Vy, and Vz. So instead of making a circle, if I take all of the vectors that have a length of, say, 20 meters per second, and I plot them in 3D space, starting from the origin, I get a sphere. And just like the length of the circle in 2 dimensions gives me my degeneracy, the surface area of that sphere gives me my degeneracy in 3 dimensions. So what we're going to do is we're going to just say that the degeneracy of a specific velocity is equal to 4 pi v squared. That is the surface area of a sphere of radius v. Notice that higher velocities will have a larger degeneracy because they have a larger surface area. So there are simply more ways of distributing your velocity if you have more velocity to distribute. So when we plug this in for our degeneracy, we find a final function for our probability of a particle, an individual particle having some velocity in a set range between, say, 20 meters per second and 100 meters per second, right? In some range of velocities is equal to this function here. And I've pulled the 1 over z out front because remember the partition function is just a constant. It is the sum of all of the Boltzmann factors multiplied by degeneracy for all possible states. And that doesn't change throughout my integral. The Boltzmann factor for the system is just a constant, so I can pull it out front here. And what we're going to do next is we're actually going to normalize the probability. That is, say, I know that the probability, if I integrate over all possible velocity magnitudes, must be equal to 1. Now that we have our general expression for the probability, we can use the fact that the probability must be normalized, that is, the probability of the particle having some velocity must be 1. And we're going to use that to find out what our 1 over z term is here, which we would call probably like a normalizing factor in quantum mechanics. So here we have this integral. It must be equal to 1. And what we're going to do is we're going to use a change of variables to get this integral into a slightly more workable form. So we're going to let a variable x equal v times the square root of m over 2 kt. Therefore, we can have dx equals dv multiplied by the same factor. Okay. Plugging this change of variables into our equation, we end up with this expression here. And pulling all the constants out front, we have this integral here to solve. And we can't actually, for arbitrary limits of integration, we can't actually come up with a closed form for this. But in the specific case from 0 to infinity, we can actually show, and Schroeder does show in the back of the book in the appendix, that this integral must be given by the square root of pi over 4. We'll talk about how to evaluate this integral in the case of not integrating from 0 to infinity, where we'll have to basically rely on computers to find out what the value of that integral will be. Okay, so solving here, we know that our integral is equal to square root of pi over 4. We therefore find that 1 over z is equal to this value here. Finally, we can write down a probability of the particle having some velocity between v1 and v2 as being given by this expression, which is simply this with our value that we found for 1 over z plugged in here. So now we can plug in any value of v1 and v2 that we would like and solve for the probability that a particle will have a velocity in that range. So now what we have is our function inside of the integral is actually called the Maxwell speed distribution. And it looks like this. So the height of the graph represents the relative probability of a particle having some given velocity, magnitude of velocity or speed. And if we want to find the probability of a particle having some speed between two ranges, we have to integrate this function, and the area of that integral gives us the probability. So the actual value of the function at any given point is not the thing we're interested in. What we're interested in is the area of this graph between 2 points. That's what gives us a probability. This function here, which we've called kind of dv, which is the same notation that they use in the book, plays the same role for this distribution of speeds as psi star psi does in quantum mechanics. So in quantum mechanics, if you square the wave function and then you integrate that between two values, you find the probability of finding a particle in some range in space. And the exact same thing is true here. Instead of integrating over space like we do in quantum mechanics, we're integrating over velocity. But the point of this function is to integrate it and find a probability. What we can tell about this function is first that as our velocity goes to zero, our probability of a particle having that velocity also goes to zero. And this is because of this v squared factor here. So v squared goes to zero as v goes to zero. And what this is telling us is that the number of ways for a particle to have zero velocity is only one, right? There's no distribution of velocity functions that have zero velocity. There's only one way to be stationary. But as our velocity increases, our relative probability increases, and that is because the number of ways of having higher velocity is larger, right? And you can think of this as kind of the v squared wins in this region here, and we kind of look like a parabola. Then, as we get to higher and higher velocities, what happens is that this exponential factor, this e to the minus mv squared over 2kt, takes over completely. And in this case, as we get to larger and larger velocities, this function here goes to zero very quickly. And so for low velocities, kind of the v squared term wins, and we get this rise. And then we have some peak. This is the most likely velocity for a particle to have, is at the peak. And then we have this fall off due to the exponential drop off here. You can see that this tail actually extends quite a ways. So even in a normal, kind of an average temperature, room temperature air, there is some probability of an individual particle having a very, very high speed. Now, the vast majority of particles have speeds, somewhere in this region, but some particles will have very, very high speeds.